4 people stand in a line, each waiting on the person beside them, and nobody can finish until the last one answers. That is exactly how a computer evaluates a recursive factorial. In this video, we act out every call, watch the answers flow back, and learn when recursion beats a loop. One more example rounds out the lecture, and it is the one we will act out. Factorial. Recall the definition. N factorial is n times n minus 1 times n minus 2 times n minus 3, all the way down to 1. To write it recursively, we start the same way as always, by finding the simplest input whose factorial we already know. The base case is the smallest input we can answer immediately with no further work. 0 factorial is 1, so returning 1 when n is equal to 0 is a perfectly good base case. The code we will write stops at 1 instead. If n is equal to 1, return 1. Either choice works as long as the recursion is guaranteed to reach it. The recursive step comes straight out of the mathematical definition. Factorial of n is n times n minus 1 times n minus 2 times n minus 3, and so on down to 1. Pull the leading n out front. Everything left behind, n minus 1 times n minus 2 times n minus 3, all the way down, is exactly the factorial of n minus 1. So the recursive step is n times the same function applied to n minus 1. The problem shrinks by 1 each call, heading straight for the base case. Here is the whole function. We call it fact_recur, and it takes one argument, n. The first line prints a message announcing which call is running. That will let us watch the calls happen. Then the two pieces we planned. The base case, if n is equal to 1, return 1. The recursive case, otherwise, return n times fact_recur of n minus 1. One line for the base case, one line for the recursive case, and the function is written in terms of itself. That is the entire implementation. To see what the machine really does, we act it out. Picture the main program as one person standing at the front holding the global scope. That scope contains exactly two things: the definition of fact_recur, just code not yet running, and one instruction: print the result of fact_recur of 4. The main program does not know what factorial of 4 is. A function call means a new environment, so someone new must step forward. A new person steps forward. Their name is fact_recur and their n is 4. With n equal to 4, they take the else branch, so they owe their caller 4 times fact_recur of 3. And they do not know factorial of 3. They call someone new. A second environment also named fact_recur with n equal to 3. Here is the crucial observation. Both of these calls are named fact_recur, yet they are completely separate calls with completely separate environments. Each has its own n, each has its own job to finish. Sharing a name does not mean sharing variables. The pattern repeats. The environment holding n equal to 3 owes 3 times fact_recur of 2, so a third person steps forward with n equal to 2. That one owes 2 times fact_recur of 1, so a fourth steps forward with n equal to 1. Look at the line now. 4 calls in flight, every one of them hung up, each waiting on a value from the call below. Nothing has finished. Not one multiplication has happened yet. The fourth call is the important one. With n equal to 1, the if branch fires and it returns 1 immediately. No further calls. Its job is trivial, but without it the recursion will never stop. The base case is what kickstarts the conquer step, passing values back up. Every function returns its value to whoever called it, and only to whoever called it. So fact_recur of 1 hands 1 back to the call holding n equal to 2, and it disappears. That call replaces its pending call with 1, computes 2 times 1, returns 2, and disappears. The call holding n equal to 3 computes 3 times 2, returns 6, and disappears. The call holding n equal to 4 computes 4 times 6, returns 24 to the main program, and disappears. The main program prints 24. On the way down, nothing could finish. Once the base case returned, every call finished, one by one, from the bottom up. Running the code confirms the story. Each call prints its message the moment it starts on the way down. So the console shows this is fact of 4, then fact of 3, then fact of 2, then fact of 1. 4 calls launched before any answer existed. Then a single value appears, 24. The prints record the descent. The returned value is the whole unwind, collapsed into one number. Python tutor shows the same picture. Frames for n equal to 4, 3, 2, and 1 all open at once, then values returning back up the chain to the original call. 3 observations summarize what the trace showed. First, every function call gets its own environment. Even when many calls share the same function name, each one runs in its own separate space. Second, variables are specific to their environment. The 4 values of n never interfered with one another, and each could change only inside its own environment. Third, the flow of control is strictly local. A call knows exactly 2 parties, who it calls next and who receives its return value. No environment ever skips around the chain. With a little thought, the same job is easy to write iteratively. This version, the iterative one, prints the same opening message once, then never calls itself. No recursion at all. Instead, it has the 2 ingredients of every iterative algorithm, a loop and a state variable. The state variable prod starts at 1 and keeps track of the answer of interest, the running product. The loop variable I runs from 1 up to and including n, and each pass multiplies prod by I. 1, then 2, then 6, then 24 for n equal to 4. Put the 2 side by side and the recursive version is arguably more readable. It looks like the mathematical definition, but both compute exactly the same answer. Multiplication and the factorial were deliberately simple, but they expose what people find trickiest about recursion, writing a function in terms of itself. Neither problem needed recursion. A great deal of code does not. Depending on how you think, either version may feel more intuitive. And since loops came first, they are usually the go-to. But one signal marks a problem as naturally recursive. You must repeat a task and you do not know in advance how deep you will need to go. Recursion keeps calling itself until it hits the base case, and you never reason about the depth. The classic example is searching a file system for a file, say set.txt. One student keeps it sitting directly in their user folder. One level, done. Another has it buried under users, then documents, then schools, then MIT, then classes, then 6100L, then sets, then set1. 8 folders deep before the file even appears. The search code cannot know which situation it will face. That uncertainty about how far down the file lives is a perfect place for recursion. Evaluating expressions has the same shape. Building a calculator means respecting order of operations, and an expression can nest parentheses inside parentheses inside parentheses. You cannot know how many levels there are until you look. Yet the innermost base expression must be evaluated first. Work inward call by call, hit that base expression, and pass results back out. Recursion again, because the depth of nesting is unknown in advance. Recursion then is a function calling itself. A base case answers the smallest input directly. A recursive step shrinks the problem toward it, and every call runs in its own private environment, returning only to its caller. When the depth of a problem is unknown, recursion is the natural tool. Next lecture recaps recursion with the Fibonacci sequence, then applies it to lists within lists within lists. Nesting of unknown depths, a perfect problem for recursion. To practice what you just learned, this course has free exercises and AI-graded feedback on ludium.ai. The link is in the description.